Hello students, I hope you're having a wonderful day. Today I would like to complete a problem with you. We're going to use Kepler's third law and we're going to calculate the average orbital distance of a moon that is orbiting Jupiter. So let's go ahead and read the problem and we will go through the calculation together. So Galileo measured the orbital sizes of Jupiter's moons using the diameter of Jupiter as a unit of measure. He found that Io, the closest moon to Jupiter, had an orbital time period of 1.8 days and was 4.2 units from the center of Jupiter. Callisto, the fourth moon from Jupiter, had an orbital time period of 16.7 days. So there's two parts to the problem here. Part A, we are required to create a sketch of both Io and Callisto orbiting Jupiter. And then in part B, we're going to calculate the average orbital radius of Callisto. So for part A, we're going to draw Jupiter. And it says that the closest moon is Io. So I'll label Io right here. And according to Kepler's first law, we know that when a moon is orbiting a planet, the planet is located at one focus of the ellipse. So let's try to draw it as accurately as we can here. And then we have the moon Callisto right here. It has an orbital time period that is approximately 4 times that of Io. I'm sorry, it's 16.7 days. So this is Callisto. So we have something that looks like that. And Kepler's third law, so it says that the square of the quantity of orbital time period for object A divided by orbital time period for object B is equal to the cubed value for the average orbital radius of object A and radius for object B, and this is cubed, okay? So what I would like to do is go ahead and remove the brackets here, or our parentheses, and say orbital time period for object A squared divided by orbital time period for object B squared is equal to the average orbital radius for object A cubed, so R sub A cubed, divided by the average orbital radius for object B cubed, so R sub B cubed. All right, and this is the form that I would like to use here. So I'll go ahead and erase the top equation. So what we need to do at this point is identify some values here. So our problem tells us that Io, the closest moon to Jupiter, has an orbital time period of 1.8 days. So I have orbital time period identified by capital T. We're going to use a subscript. So sub Io to help us describe the orbital time period. This is equal to 1.8 days. And it has an average orbital radius of 4.2 units. So R sub Io is equal to 4.2 units. And remember, this unit of units describes the diameter of Jupiter. Next, we have the orbital time period of Callisto, and this is 16.7 days. And then we have the average orbital radius of Callisto, and this is the center to center distance. We don't know what that is, but we know that we are going to have a unit of units. And remember, that is the diameter of Jupiter, okay? So what we're going to do is we are going to plug our variables here into our equation. Now, one thing that I would like to point out is thinking about this strategically, we want to make this problem as easy as we can. So I would recommend placing the unknown in the numerator. So whether your unknown is orbital time period or average orbital radius, you always want to place your unknown in the numerator. The reason for that is you can isolate your unknown by simply multiplying by the denominator on both sides of the equal sign. And so, for example, if I multiply my denominator on both sides of the equal sign here, I get the average orbital radius for moon B cubed over here. So that's going to cancel on the right-hand side, and then that's going to place it over here. Okay, so that's very simple. That's one step to isolate r sub a cubed here. So what I'm going to do is I'm going to say that the average orbital radius for Callisto is going to be my unknown. So according to Kepler's third law, this is r sub a. We're going to have r sub Callisto here. Okay, so setting our problem up, what we're going to have is orbital time period of Callisto squared divided by the orbital time period of Io squared is equal to the average orbital radius of Callisto cubed divided by the average orbital radius of Io cubed. Okay? So once again, we're simply going to multiply both sides of the equal sign by the denominator here. And so on the right side of the equal sign, r sub Io cubed will cancel. And then we're going to bring it over here since we're multiplying. So we've isolated r sub Callisto cubed. And I'll just rewrite the equation so it's clear here. In my numerator, average orbital radius of Io cubed multiplied by my orbital time period of Callisto squared divided by the orbital time period of Io squared. Okay, there we go. All right, so now what I want to do is fill in some values here. So in my numerator, average orbital radius of Io cubed, we've written this value down here. So 4.2 units cubed multiplied by average orbital radius of Callisto, orbital time period is 16.7 days. And we're going to square that, divided by orbital time period of Io, 1.8 days. And we're going to square that. So I'm going to erase to free up some room here. All right, so we need to get our calculator out here. So in my numerator, so 4.2 cubed is going to be 74.008. And remember, not only are we cubing the numerical value, we're also cubing the unit value. So I have units cubed. We're going to multiply this by 16.7 days squared. This gives me 278.89. And we have units of days squared. We're going to divide this. So 1.8 squared is 3.24 days squared. Okay, let's go ahead and resolve our numerator. So I have 74.088 times 278.89. This is going to give me 20,662.4. And then our units are going to be units cubed times days squared. So units cubed days squared. We're going to divide this by 3.24 days squared. And let's talk about the units right here. So in my numerator, I have units of days squared. In my denominator, I have units of days squared. They're going to cancel out. This is going to leave us with the unit of units cubed. So 20,662.4 divided by 3.24 is equal to 6,377.28. And we have units of units cubed. Okay? All right, so on the left-hand side of the equal sign, we have the average orbital radius of Callisto cubed. Well, we're not finished with the problem because we're required to take the cubed root of this. So when we take the cubed root, that will cancel out with the cube here. So what I'm going to do is take the cubed root of the average orbital radius of Callisto cubed, okay? We're going to take the cubed root of the right side of the equal sign, 6,377.28 units cubed. And so we're taking the cubed root of our numerical value and we're taking the cubed root of our unit value. So on my graphing calculator, I know many of you are using a graphing calculator. We have to surf through 4 or 5 different menus just to locate the cubed root function. So what I would recommend, just to make this easy, is to use your parentheses. Let's type in our number, 6,377.28, close parentheses. Let's use the caret key like we like to describe it. So our exponent key here, open parentheses. Remember, we're taking the cubed root, so this is 1 divided by 3, close parentheses. So in the exponent, we're taking it to the 1/3. Okay, so let's do that. So open parentheses, 6,377.28. Close the parentheses on your calculator. Use the exponent key. Open parentheses. Don't forget the parentheses here. So open parentheses, 1 divided by 3, close parentheses, and hit enter. And this is going to give me 18.544. Okay, so we've done that for the numerical value. Now we're taking the cubed root of the unit, which is units cubed. So that's just going to be units. And remember that this unit describes the diameter of Jupiter. Okay, and so the problem is asking us in part B, using the same units that Galileo used, predict Callisto's distance from Jupiter, okay? So what we're talking about, distance is average orbital radius, okay? And this distance is center to center, and we are identifying this as R sub Callisto. Okay, this dimension here, and this is 18.544 units. Okay? All right. Well, I hope I've been able to help you today with using Kepler's third law. If you have any questions, you can send me an email, contact me over Canvas, or just call me in my office. Thank you. I hope you have a wonderful day.